Hi, this is Greg from Structural Toolkit, and this is the third video in our two-story residential house design series. In our previous video we went through our bracing loads and design, and now we're up to our upper roof design. Our approach will be to design each roof member, in our case each lintel, as a series of isolated beam designs. To do this we'll be using Structural Toolkit with the project we had started last episode. As we discussed previously, trusses are typically handled by the manufacturer, so we won't be designing any of them. And although we will be designing the columns under each of our lintels, we won't be looking at any other stud framing unless it's over 3 meters high, as any stud walls 3 meters or under are covered in AS 1684 for all standard loading scenarios. Now, typically speaking, all of our beams will be designed as simply supported, spanning from center to center of pinned supports. Most of the standard beam to column or beam to beam connections in a residential house transfer little to no moment, and so this is a reasonable approach. From a beam design point of view, this approach is also generally conservative, as by allowing rotation at the supports we will end up with a greater midspan moment and deflection. That being said, many of the connections will have an eccentricity from the fixing of the beam to the face or top of the column, and so any moment caused by this will need to be considered in the column. We talk about this in detail in our timber column design video. In our beam design video, we went through the various beam design modules available in Toolkit, which you can refer back to as needed. For our lintel designs here, the most appropriate module will be the roof beam module. Before we get into designing each lintel, we want to first make sure we have our design wind pressure set as the default for all our modules, which we can do using the project values feature, where we can create the wind variables and edit it to our wind pressure of 0.68, which we calculated in the previous video. Have a look at our project values video if you want to find out more about this feature. The house project value will also be applicable here, so we'll create it as well. This variable will set the house option in timber designs to yes, affecting the roof live load and various short and long term factors. With our project values set, we can now open up our first roof beam design. But before we'll do that, we'll create an upper roof section to the left here. Now, as a reminder, here is the upper roof plan that we set out in the first video of this design series. We have 9 lintels in total, and we'll be starting with the first lintel at the top left here. Our roof comprises of sheet roof over timber trusses, and our lintels will be within lightweight clad timber stud walls. We'll call our first lintel UL01. Designating it this way will make sorting our designs in our project easier. So our first input is our category. Now, to keep things simple, the approach we will be taking with this is category 1 will be for any repeating members such as roof rafters or floor joists, and category 2 will be for any lintels, roof or floor beams. This category will predominantly affect your fire factors. They're outlined in AS 1720, and we also have a description of each to the right here. Our span will be our centre to centre of a double stud or column, which measures up as 2090 mm, which will round up to 2100. Our centres is then just the load width of roof on our lintel. We'll measure this from the edge of our gutter to the ridge point as our roof is symmetrical. This gives us 3.8 meters. Providing our lintel isn't too far below the top plate of the wall, our LAY will be our truss centres, which is 900 mm, being the spacing of lateral restraint. This restraint is typically going to be on the top edge of our member, being the compression side. As discussed earlier, our span type of our members will be single. Next we can then move on to our loads. AS 1170.1 Appendix A gives some standard weights of various construction materials. Typically for a sheet roof like ours, comprising of trusses and plastered ceiling underneath, a dead load of 0.4 kilonewtons per metre squared is taken, being 0.4 kPa. Our roof dead load input already defaults to this number, so we can leave it as it is. It's probably worth mentioning here that although technically the trusses themselves are going to apply point loads at 900mm centres along the beam, providing the beam is long enough, idealising it into a UDL is much more convenient. We'll look at this more with a shorter lintel. Our next dead load to consider is our wall load above our window. Having a look at our elevation, we can see this measures 300mm to ceiling height. The weight of 90mm stud-work and lightweight claddings can vary, but we'll use 0.5 kilonewtons per metre squared. So we'll put in 0.5 in our second dead load input. And then change our centres here to be 300. Where in this case the load width is the height of the wall. For clarity, we'll also rename the dead load to wall dead load over to the right. Next we have our live load, which has already been automatically determined based on the value above. We can delete the second live load input and leave our alternative point load as is. We get a live load of 0.25 kPa and a 1.1 kilonewton alternative point load due to us designating the member as house. This comes from note 3 of table 3.2 from 1170.1. Finally, we have the wind load, which includes our new default of 0.68 kPa. We can see here how useful the project values can be, and it will make sure we never miss these values, especially in a case where your wind load may be greater than the standard default. As for our wind shape factors, CPE and CPI, we'll be taking some commonly adopted values for residential design of 0.9 external and 0.2 internal, with positive being upwards. These values come from the wind code, and you'll find they are typically the critical values for a house of standard geometry. You can also look at AS 4055 for more examples of these values, but do note that we are not using 4055 for our design here. These two shape factors we'll be using on all of our internal roof members. This can be a conservative approach, but the idea is to limit the amount of unnecessary effort in design. Generally, the wind load case is not critical, so optimizing the CP factors is not overly beneficial. If it were critical, then you could start looking at refining the values. This idea is similar to why we just adopt the critical designed wind pressure. As we have decided to take our loads as UDLs rather than a series of point loads, we don't need to add any further point loads here. And so we can move on to determining our member size. There are countless timber grades and types out there, but we'll be keeping to just a select few. F7 KD Pine or MGP10 will be our first choice of timber, and we'll be using this wherever possible. If pine isn't going to be feasible, then we'll use F17 KD Hardwood instead. And finally, for some of the larger timber members, engineered timbers such as LVL15 may be required. When F17 or engineered timbers are no longer feasible, you may also start looking at steel members instead, though keeping things as much in timber as possible is typically preferable. So looking at our current lintel, we'll be starting with F7 pine. So we'll select that and start with a 140 by 45. Right away we can see this won't work, so we'll use the arrow to the right to bump the size up. For deflection, we'll want to aim for span on 300. Details on suggested serviceability limits can be found in AS 1170.0 Table C1. By bumping our size up twice to a 190 by 45, we can see we're now within all our limits. Often engineering drawings will provide alternative grade equivalents to give the builder more options when selecting timber. In our case, we might say that F7 KD pine can be substituted for MGP10. But to make sure that an MGP10 equivalent is within the limits also, you can either switch to it by using the select button or by using a button at the top of the member tab to quickly switch between. We can see in our case that MGP10 also works fine. In the case of MGP10 and F7 KD pine, you usually only need to do this when a design check is quite close to the limit. For example, when the moment utilization is over 90%. MGP10 has a greater shear capacity, but the bending capacity is reduced for smaller sections, which is why we need to check this. And with that done, our first member design is complete and we can move on to the next one. Rather than starting a beam design again from scratch, we can just copy our current one and then change the inputs, as several of the loads will be the same. Another way about this is to set up presets that cover various typical design cases. We went through presets in our useful features video, so have a look at that if you're interested. So we'll copy our UL01 and go with the suggested name of UL02. Our span this time is 1410, which will round up to 1450. We spoke before about idealizing our truss point loads into a UDL when the beam span was sufficiently long. Well, in this case, our beam isn't sufficiently long. You'll find that when a beam span is less than 2 times the centers of a truss or rafter, you'll end up with a greater design moment with a single mid-span point load instead of a UDL. So what we'll need to do instead is convert all our loads except our wall dead load into a mid-span point load. We'll set our centers to 0. Typically under this scenario we would have an LAY of half the span, but if we look at our elevation we can see the window is much lower than our previous window. Often lintels are placed at the top of the wall, with the wall below supported off it, but in the event the lintel is placed at window height, it would be better to set our LAY as the span of the member. Measuring our wall height, we get 700 millimeters. We can then delete our other loads to keep things clear. And in our point load cell type, calculate our point load for each case. We know we had a 3.8 meter load width, so for our dead load we'll input 0.4 kPa multiplied by 3.8, which is then multiplied by our truss centers of 0.9. We'll then do the same for our live load of 0.25 kPa. However, as this is less than our alternative point load, we'll go with 1.1. Finally, we have our wind load, which is similar to the rest, just with our ultimate wind load and shape factors applied. We also need to make sure it's negative for upwards. Our position will be in the midspan, which is generally the default value, as we can see to the right. It's probably worthwhile now to talk about our shear using the point load at the support option. As default, this is set to yes, and effectively means that any point load used in this module when assessing the design shear force will be placed at the support. The idea behind this is that often roof systems, such as trusses, are coordinated by the builder and designed by a manufacturer at a later date, meaning the engineer isn't going to know where exactly the roof trusses will land on any structural member they're designing. So by having it set as yes, if the truss does end up landing close to support, we will have appropriately accounted for it in our design. Before we look at our member size, we'll also add a comment to our point load stating the load area we used to ensure clarity with our design. An easy way to do this is to right click and go insert comment from cell, which will convert whatever we put in that cell into a comment. Looking at our member size, we can see we can possibly bump down the size a bit, down to a 140 by 45. At the moment we have it on MGP10, so we'll switch it back to F7 with the button on the member tab. And with that done, our second lintel is complete. Our next lintel is then slightly different again. The loads will be most similar to our first lintel, so we'll copy that to make things easier. Our span is going to be 3100. Our centers this time will just take as one truss center, being 900. You could possibly justify using either 450 centers or even none, depending on how the roof ends up being framed, but as we don't know for sure, it's best to be conservative. Given the lintel is going to be close to the ceiling, even though there isn't lateral restraint provided by trusses landing along the span, the roof structure itself will provide some. So rather than taking our LAY to be the entire span, we can probably justify taking half the span. Our wall dead load will be slightly different to before, as we now have a triangulated load to deal with. One approach here is to take 2/3 of the height of the wall as a UDL across the entire span, which in our case is 2/3 of 1960, which is about 1300. Just remember when it comes to reactions to think about the way you distributed this triangular loading. The rest of our loads are good as they are, so we can now look at our member size. We can see our 190 by 45 F7 KD pine isn't going to work, so we could bump it up to a 240. However, that is getting a bit big for a lintel this close to the ceiling. What we can do instead is look at an F17 KD hardwood. Which will work fine as a 190 by 35. The rest of our lintels follow a similar pattern to the three we've just designed, so we'll skip ahead to the point where we've got them all completed. So with our lintels all designed, it's now probably worthwhile at this point to touch on wall tie design. For standard size windows and floor to ceiling heights, usually you don't need to worry about this too much, as a standard 90 by 45 MGP10 top plate will be able to do this job fine. However, one window in our upper floor in particular is probably worth looking at, being Ep.3, as it has quite a large span and also some distance below the window. To design a wall tie, we can use the wall tie module. Our span will be the same as our lintel above, being 3.1 meters. Our centers will take us mid-height of the window to halfway between the floor level and the underside of the window, which is half of 2400. Our LAY will be our jack stud spacing, which is typically 450. For our loading section, our project value wind load is brought in, and the CPE and CPI factors default as critical values for inwards and outwards wind action on a wall, so we'll leave them as is. For wall ties and stud framing, we'll be looking at a deflection limit of span on 250, which will change below. We'll first try our typical 90 by 45 wall tie and see how we go. We can see that this size will not work, so we'll then try a double plate instead, which does work. All our other windows are no longer than 2100, so a standard plate will work in these cases. If you end up with a wall tie design that doesn't work as a single or double 90 by 45 MGP10, and you use say a double 90 by 45 F17, then you will probably also want to look at your columns supporting these wall ties for mullion action. So with all our upper lintels and wall tie designs complete, we can now look at designing our upper columns. To keep things organised, we'll create another section in our project. One of the commonly used columns in a standard house is a double 90 by 45 MGP10, and wherever possible it will be our go-to column. The next step above this is a double 90 by 45 F17 KD hardwood, which we'll use where an MGP10 doesn't work. There are other timber options such as LVL, but we'll talk about them whenever the time comes that we need to use them. So a quick way to go about designing our columns is to just work out what the maximum load each of our column types can take, and then assign the columns to each lintel where the reactions don't exceed this maximum load. We'll start with our MGP10 column, which we'll be calling column DS01, where DS refers to double stud. To design our timber columns, we'll be using the columns module. Now, as we will be designing some columns of different height in the upper floor due to the stair landing, we'll also add to the name 2700. To designate, it's going to be 2700 high. The approach here is similar to that of our beam design. We'll be designing our columns with pinned ends, and so effectively no moment transfer, other than for any eccentricities we might want to consider, which we will talk about later. Due to the nature of stud work framing, a pin support approach is common and simplifies design. It is, however, always important to understand the connection you're using and justify the pinned approach if you use it, as certain connection types will inherently transfer moment, such as a bolted end plate, so you don't just blindly pin everything. We did a video on this module previously, which may be worth a review as needed. As our column is going to be supporting a Category 2 member, we'll leave it as Cat 2. For our house option, as we are looking at the roof at the moment, it doesn't actually matter for this design, and when we change our live load type below to roof, this option will disappear. We know our floor to ceiling height is 2700, so we'll leave it as that. Our strong axis effective length is going to be our length, as there are no internal and external side restraints. Our weak axis effective length is then going to be typically our noggin spacings. For a 2700 high column, there will be at least one noggin, so we'll set it as 1350. For reference, AS 1684 sets the maximum noggin spacing to 1350 as well. Our LAYB is then going to be the same as our minor axis effective length. As we can see, it defaults to this value at the moment, so we can leave it as it is. As our column is going to be part of stud framing, we can also leave our effective length factor as 0.9. Next, we have our compression loads. As we discussed, we'll be trying to work out the maximum load our DS1 can take. But before we start altering these loads, we'll first go through our other inputs. A live load duration is going to be roof, as all our upper floor columns are supporting roof loads. We then have our moment inputs, which we will take as the default, where our actual loads are eccentrically taken to the face of the column, causing a moment. We talked about this in depth in our timber column video. Now that we've covered all the inputs, we can start altering our compression loads. As discussed, we'll be trying to work out the maximum loads each of our column types can take. A good approach for domestic loads is to make the dead and live load the same and increase them until we have full or almost full utilization of the column's capacity. In our case, we'll be interested in the combined action ratio. So we can see that a dead and live load of 6 kilonewtons will get us pretty close. With experience, you will get a good feel of what load standard column sizes can take, so it will usually be pretty quick to work out each design. Wind uplift is also something you may consider, but you will find that unless you have an extremely high wind uplift, you won't need to consider it in this part of the design. With our maximum load found, we can now move on to our next column type. The easiest way to do this is to just copy the one we've already done and name it DSO2. In here we can then change the section type to our F17 Katie hardwood, and then bump up our loads, which for a 2700 high column will typically get you to 13.5. Given the lightly loaded nature of our upper roof, there's a good chance we won't need this type for this length, but for demonstration it's worthwhile to show. The final column design we'll be doing for this floor is the column in the stair landing. We'll start with the DSO1 and see if we can get it to work with just that. Measuring our floor to ceiling height, it's 3800. So we'll include that in the name. We'll change our length to 3800 and keep our LAY as 1350. We can see our column understandably no longer works. Reducing the load down a bit, we should be able to get it to work as 4 kilonewtons. Opening up our reaction summary at the top. We can see that the lintel in question for this column, being UL02, has a reaction of only 1 and 0.6. To account for the alternative point load being possibly anywhere on the span, we would usually increase the live load reaction to 1.1 kilonewtons in this case, so we'll end up with 1 and 1.1. Which works comfortably for a 3.8 meter high DSO1. As expected, none of the other columns have exceeded our DSO1 2.7 meter capacity either, so it looks like we'll be able to use a DSO1 for all our upper columns. However, one thing you need to consider is any mullion action on the columns. With our eccentric moment approach in column design, we typically don't need to perform any mullion designs unless the wall height exceeds 3 meters, or unless some of the windows are significantly long. In our case, we do have the DSO ones that are in the stair void that are over 3 meters. So we'll perform a mullion design for them. Effectively, we'll be designing this column as a mechanism to get the wind pressure applied on the wall into the roof and floor, which can then transfer it into the brace walls that we went through in the previous video of this design series. We'll open up a mullion design module and name it mullion DSO1 3800. This module is similar to our column module, but instead of the moment input section, we have an inwards and outwards wind UDL section. We'll put in our length of 3800. Our centers will be from the middle of the window, as on the other side of the window will be our other mullion, and to the midpoint between the next stud along to the left. Typically, the spacing of external load-bearing wall studs is 450 millimeters, so we'll go with half of that. The midpoint of the window to the midpoint of our column measures up as 705. So adding on half of 450 gives us 930, which will round up to 950. Our LAX will be 3800, as with our column design, and our LAY will be 1350. In our loading section, we'll put the capacity load we used for our previous 3800 DS1, being 4 and 4. And also change our live load duration to roof. As we are using project values, our wind load is already in there. Our default CPE and CPI factors are critical values for external walls, which you can find details on in the wind code. These values should do the job for us. If needed, there's also a point load input down the bottom. In our case, we'll be idealizing our loads to a UDL, so won't be using it. Looking at the top, we can see that our combined ratio is just a bit over, which you could probably justify by lowering our compression loads. However, our deflection is also quite high. Our default deflection limit is currently spanned on 250. You may be able to justify a lower limit. For example, 1170.0 suggests height on 200 for plaster walls with face loading. However, an important part of deflection design is also considering any cumulative deflections that may occur over the house. For our design, we'll stick with our default of span on 250. So as our column isn't going to work as a DS1, we'll need to come up with an alternative solution. One option might be to make our column a triple stud, or we could try using a different timber grade. For our design, we'll try upping the column to a F17 KD hardwood, being a DS2. Which we can see works comfortably. Now, to keep things consistent, we'll rename this design to DSO2. And also redo the 3800 column design. An experienced engineer may have already anticipated something like this, and so may not have needed to go through all these additional steps. But for the purpose of this video, it should help showcase the iterative nature of engineering. Now, usually you would also have to design some studs to go between our column and the internal return walls at the edges of the stair void. However, as the distance is only 450 millimeters, we won't need to add an additional stud in between. If it were greater than 450, you might either design some studs using the mullion design or provide a wall tie between the return walls and columns, so that you can still use standard framing in between. Or you could even design a wall tie that spans the entire void, meaning you won't need to design the mullions that we did. Now, the final thing to do is check off each column for the size they need to be. There are many ways this can be done, but the way we will be doing it is by creating a plan in CAD and annotating the reactions on each of our columns. In our case, things are quite simple, so you could justify not doing this at all, but we'll do it anyways to give an idea of how it's done. With our plan here, we've also added a legend down the bottom showing the capacity of each member type. You can then use this to check off each column to ensure that they are the appropriate size. When column loads and systems get quite large and varied, this is a very useful process. We'll see this in action when we get to the lower framing design. With our columns now designed, our upper roof framing and wall design is complete. All our timber connections would fall under AS 1684, so we won't be designing any of them. That being said, larger spans may end up with significantly high uplift, especially when the roof is lightweight sheet, in which case specifying the hold down straps and nails or screws is necessary. So with our column design complete, we have finished all the design necessary for the upper roof and wall framing. In our next video, we'll go through designing the floor and lower roof framing and columns, and will be based on a lot of the concepts we've gone through in this video. If you have any questions, feel free to contact our support team via email or by calling us. Thanks for watching.